So today we are happy to have Michael Lee as a Lima seminar speaker. So he got a PhD from Oxford and Ford and is now postdoc at the Harvard University. So he works on some field theoretical aspect of the particle phenomenology. And today he'll tell us about his method for scans. Right, very useful.
Yeah, thank you for the invitation. It's very nice to be here and all of you. And yeah, thanks also for the introduction. As basically mentioned, I'm going to be talking about scans. This is a recent paper together with Lisa Randall, and it's the archive link here. And we're looking at anomaly mediation in supersymmetry and supersymmetry breaking in extra dimensions is sort of the broad theme of the talk. But we'll sort of get into the specifics in a bit. Before getting into the details, I just want to sort of motivate a little bit why we're sort of thinking about extra dimensions and supersymmetry. Both of these I should also say, maybe just before I start, I'm going to sort of gloss over some technical details, so hopefully it will be accessible, but I understand that there's sort of people here from different backgrounds, so if you have any questions, please do stop me. I'm happy to answer at any time. But I sort of want to motivate just in general why we're thinking about sort of extra dimensions and supersymmetry. These are sort of popular topics maybe 25 years ago, but they're sort of a bit out of fashion now with null results that collide us from a phenomenological perspective. But I think part of the original motivation, at least from my perspective reading the literature a long time ago, was to study these phenomenological models which incorporate either extra dimensions or supersymmetries, because these are both ingredients for string theory, at least for phenomenological compactifications of string theory. So if we believe that's like the theory of quantum gravity, which describes our universe, then there are two ingredients which will inevitably play a role, at least at some scale, in describing sort of the standard model in the low energy. So if that's still true today, at least again, as far as I know, all of the models that people write down for string theory, which have some either reproduce the standard model or have some phenomenological implications, are supersymmetric, and they all have extra dimension. And within that, there's sort of two big problems well, probably more than two, but two main problems that come from trying to connect string theory to low energy observables is the issue of moduli stabilisation. So in string theory, you have very many extra dimensions. Their sizes are set by scalar fields, which are known as moduli, and they need to be stabilized. You need to have a potential which fixes their value. Otherwise, they will sort of run away. The extra dimensions either become large or shrink to zero size in the presence of some energy density. So there has to be some sort of mechanism to stabilize these extra dimensions. And obviously the low energy world that we observe is not supersymmetric, so supersymmetry must be broken. And that's true. So in order to connect sort of UV complete theories to observables, you need to incorporate these two effects, but in a fully sort of string theoretic setup, these are quite difficult questions to answer. And there's sort of a few known models, but the sort of a sort of complete way of doing this in general is not really known. So perhaps by just studying sort of simpler scenarios which incorporate these two features, so supersymmetry and extra dimensions, can maybe shed light on the bigger problem in string theory. Another sort of phenomenological motivation, which is not really going to touch on as part of this talk, is sort of stabilizing the electroweak hierarchy. So both extra dimensions, at least warped extra dimensions and supersymmetry, have been proposed as solutions to the hierarchy problem. That's sort of a more phenomenological motivation why you might consider these types of things. Okay, but my actual talk is going to be something a bit more specific than that. I'm not going to talk about string theory or the hierarchy problem. but I'm going to just consider a 5D model. So we have, and we have sort of an extra dimension, the coordinate I'm going to call y, and it's an interval bounded on either side by two branes, so 4-dimensional boundaries, the IR brane at y equals pi and the UV brane at y equals to 0. And in any number of dimensions greater than 4, the minimal supersymmetry in the bulk theory is n equals 2 from the perspective of the 4D theory. So has an extra supersymmetry in the bulk, and this supersymmetry is broken by the discrete spacetime symmetry. So the way we construct this interval is we have a circle, and then we quotient by a discrete group, this Z2, this is called an orbifolding, and then it breaks the n equals 2 symmetry to n equals 1. So see more in more details how this appears. But this is also to motivate this 5D setup. This is some analog of this is also at play in string models when to break. They have the same issue. You have some extra dimensions. You have an n equals 2 theory, which is also not chiral, so it can't be the theory of our world. So, but you can break it by some discrete symmetry, discrete spacetime symmetry to an n equals 1 4D theory. So it incorporates that feature as well as the extra dimensions. And we have also localized degrees of freedom, which can live on either of the branes, which is again something that's spectral. And this modulus R, the radius of this S1, is or also referred to it as the radion. This needs to be stabilized. So in this theory, yes.
Sorry, so are you identifying the left and the right boundary? I'm confused because you have different names, like left hand side you have UV brane and on the right hand side you have brane.
So I guess the no is the answer. This is already with the quotient out. So this y would be the angular coordinate to go from 0 to 2 pi.
Yes.
The quotient by half, and they go 0 to pi. So I can just draw the picture. It's maybe easier. So if I have the full circle like this, and I'm going to define my angular coordinate from this axis, the Z2 identifies this point with this point here. So then I keep this whole interval, this upper half, and I have two fixed points at pi, which don't change on the Z2, and at y equals 0. And that's these 2 points. Okay. So the point here is that this setup also does capture a lot of these ingredients which are there in a string theory set. But I'm going to focus on one sort of specific aspect of supersymmetry and extra dimensions for most of it, and that's anomaly mediation. So this is a bit of an overview of the talk. I'm going to first discuss anomaly mediation in 4D. And the reason for looking at anomaly mediation is because it really works. It's most natural in an extra dimensional setup. So I'll just describe how it works in 4D and then discuss how, if you just sort of think just in some toy models, what the issues might be with going from the 4D answer to an actual 5D setup. And basically the issues are that if I do an effective theory in 4D, which I'm supposed to reproduce the extra dimensional setup, whether or not the extra dimension is warped means you get completely different answers. So I'll explain that in more detail, but that's one thing. And the other thing is that the 4D theory can never really reproduce the boundary terms and the couplings between the bulk and the boundary. So we have sort of distinct theories which live on each of the branes and in the bulk in the 5D, whereas the 4D theory does not reproduce. So there's some issues there. And then I'll talk about the 5D setup, how to stabilize it. The sort of important thing will again be the difference between things in the bulk and on the boundary, and also the role of what's called the no-scale form of the Kähler potential. So I'll explain what that is, and then I'll finish by giving the sort of answer, the final answer of what happens in the 5D theory and how it differs from the 4D theory. So this is sort of the focus here is on anomaly mediation, this sort of specific way of communicating supersymmetry breaking. But actually in starting with the extra dimensional model and going to a 4D thing, we'll find some sort of general results, issues with these type of theories, which are not present from just doing the 4D analysis, which is sort of I guess the main point is like, why do you need to actually consider the extra dimensional thing in the full sort of setup, full generality? Okay, but first of all, I'm going to go for a bit of a review of anomaly mediation and also supergravity along the way, because anomaly mediation is a gravitational effect. So this is sort of the supergravity Lagrangian in 4D. And I just want to, at least written in what's called the compensator formalism. So we have this field called a conformal compensator. And I'm going to put the subscript 4 here to say that we're in 4 dimensions. So it sits at the front of this this function f. So these terms here are responsible for the kinetic terms. And this f is related to k here, which is the Kähler potential. So that's just the terminology. The Kähler potential. And so the compensator, its scalar component is fixed to be the Planck scale. And it has this f term, which will be responsible for anomaly mediation. So this f of the compensator is an important quantity. And then I have these potential terms. So this script w gives me the field strength for gauge bosons. So and then I have a superpotential, which is w, which is a function of what are called the chiral multiplet. So the chiral multiplet has a scalar component, a fermion, and it also has an auxiliary field, f. And if these f's are non-zero, that means you've broken supersymmetry. So there are an order parameters for supersymmetry breaking, you're turning on these f's or phi. Whereas this FC is not in general, but it is responsible for communicating supersymmetry breaking in the anomaly. Okay, any questions about this? Yes.
Is the comma after QI dagger in F a typo? It looks like you have a function of 2 arguments, but I don't think that's what you mean.
I think it is in general a function of 2 arguments. I mean, if the Q's are charged, then they always have to come as a product. But I think if you're singlets, they can be in general a function of both. Sure.
Well, okay, I guess I don't. But then you later write that F is minus 3 F minus K over 3.
So this K is a function of the same arguments. I guess I read it slightly with the notation. Okay, but the main thing for the anomaly mediated story is this FC, which will turn out to be related to W, the vev of W, I guess. So W can also have a constant piece. Yeah, and then I can give on this thing. So you can solve. So the way to sort of relate this sort of supersymmetric setup to more familiar things like the potential, like actual physical potential and the kinetic terms, is you integrate out these F's. So these F's are not physical fields. They don't have a kinetic term. So these F's, you solve for them in terms of the physical fields and then substitute everything back in. And what you end up with is that the F term for the compensator, that should have a 4 subscript, is related to W, and the F terms for the chiral multiplets with this derivative of the Kähler potential. And the scalar potential from ignoring D terms is given by this. So the main thing here is that we have this Kij is the same matrix that sits out the front of the kinetic term. So it's positive definite, and it multiplies this F, the F's of the chiral multiplets. So this is a strictly positive quantity. And then we subtract off W. So W should be a function of the Q's. So in order we need some of these F's to be non-zero to break supersymmetry. So that's going to give a positive contribution to the energy. And then we need to because we know we live in flat space, we want to tune the minimum of this potential to be at 0. And so that requires that W squared is related to these F's. So the only way we get a negative contribution to the potential is by the superpotential taking a non-zero value. Okay, and that also means that FC is non-zero. And in general, unless there's some cancellation between these terms, FC is going to be of the same order as these F. So these Fi's are the ones from the chiral multiplets, and they break supersymmetry. The FC does not in general necessarily break supersymmetry, but it's going to be of the same order because of this requirement that we end in flat space.
So I'm just forgetting something. Isn't there a DW term somewhere hiding?
Yeah, the F's, I haven't told you what the FIs are. They have, when you solve for the FIs, it will be like DW, DQI.
Oh, so for the rest of the, okay.
Yeah, so I haven't written out the expression. Yeah, so whatever these F's end up being, you have to tune this to zero. Tune the CC to zero, which is this. And then that tells you that the FC would generically be of the same order as the others. Okay, and this FC is going to give anomaly mediated masses. And they have the reason why the sort of appeal of anomaly mediation from a phenomenological perspective is that we have one FC, which is one dimension for scale, sets all of the masses up to things that you can calculate from just the IR. So it's very model independent, but the masses all come at loop level. So if I just go back here, so if this tau here was the gauge coupling, and so I'm going to give you the example of the anomaly mediated mass for the gauge which lives in this field strength with the gauge boson. So if I expand this to loop order, basically wherever I have a dimensional full parameter, I need to scale it by the compensator. The compensator is a spurion which couples to scale invariance. So when I do this expansion, I have this ratio here, and then that leads to a mass term which is proportional to the beta function of the gauge coupling times this dimensional full scale. So this is the mass for gauge nodes. And you can do the same thing for sleptons for other fields, but they have the same kind of form. There's this FC, which is determining their overall scale, and then they're suppressed by beta functions or anomalous dimensions, basically the running of some parameter. And so, yeah, and all of that can be calculated from just within the IR theory. And then you up to this overall scale. Okay. But these masses are all suppressed by multiple things. They're suppressed by couplings, some loop factors, 1 on 16 pi squared, and some FC, it's divided by m plane. So these masses are not typically large. And so to have anomaly mediation be relevant at all, you need to suppress direct couplings of some SUSY-breaking sector to the standard model or the MSSM fields. So if I imagine X was some field in a hidden sector which broke supersymmetry, so it has a non-zero F term, and there was some high dimensional plane suppressed coupling to Q, where Q could be a standard model field, then the mass here is just of order from this coupling is of order the SUSY-breaking scale divided by plane squared. So it doesn't have the additional suppression of beta functions and loop factors that you did for the anomaly mediated. So in a typical model where you just have where these couplings are present, then the anomaly mediation is almost always a sub-leading contribution. Unless the model has a very specific form where this function f can be cleanly separated into a visible and a hidden sector. So it means you don't have operators like this which talk between the two, and the same as the superpotential. And this is called a sequestered form. And that when the theory takes this form is when anomaly mediation is most relevant. But this is sort of a finely tuned or a tuned scenario. You have to just by fiat set all of these things, all of these couplings to zero in just the 4D theory. but you can make this sort of more natural in extra dimensions by physically separating the two sanities. So if I think, I don't have a picture here. So I think back to the original picture, I had this extra dimension separated by two branes. If I put the standard model and the SUSY-breaking sector on different branes, then these couplings will be suppressed. So anomaly mediation sort of makes the most sense in a theory with extra dimension, but almost all the studies of anomaly mediation done to date have been done in the 4D effective theory. So even if you're appealing to extra dimensions, it's still the analysis has been done in 4D. And next, I'm going to just present some sort of toy models which will help to indicate why that might not be sufficient to capture it. But if there's any questions at this point, then maybe it's a good place to. Yeah. So again, so I have the same picture, the same from one of the first slides. We have this is the setup that we're considering. The extra dimensions bounded by two branes have R is the size of the extra dimension, and the metric I'm considering is this warp product. So it's the G mu is the 4D metric. It comes with this overall warp factor, and then you have the metric of an S1. But depending on whether or not K is equal to 0, so if K is non-zero, then the bulk theory is ADS space. It's 5D ADS. K is 0 means you just have 5D flat space. So in the flat case, the radion R appears in the 4D theory as this field sigma, again, I'll put the subscript 4 to mean 4D, and it has this F, this Kähler function is just given by sigma plus sigma dagger. And this is called a no-scale form of the Kähler potential, which will be important. But in the warped case, the radion comes in this superfield, which I've called rho, which is the exponential of K pi R. And it comes with 1 minus rho squared in this function F. And the important point is there's a quadratic term here, whereas here you only have linear terms. And the fact that you only have linear terms, when you ask what happens to the F term for the radion and the F term for the compensator, if I just let W be a constant. So in this case, the equation of motion for F sigma 4, because it only appears linearly, it sets this Fc to 0. F sigma is non-zero, it's equal to W. The potential vanishes identically. And I've already said that. So you have the potential is exactly 0. So we haven't stabilized the extra dimension yet. Supersymmetry is broken by F sigma being non-zero, and Fc is 0, so there are no anomaly mediated masses. And if you contrast this with the warped case, in this case we have F rho is still non-zero but proportional to rho. Fc is equal to W, which is what you would just sort of naively express from the 4D theory. And the potential is negative. I mean, it's unbounded. But that's again because we haven't stabilized the extra dimension in this sort of toy setup. But we have a strictly negative potential. I mean, if rho is 0, then this is not at the maximum of this potential, then supersymmetry is unbroken, and you do have these anomaly mediated masses. So these two things look completely different. And if you take the K goes to 0 limit of this theory, you do not reproduce the flat case. And if you're just if I never told you anything about supersymmetry, then, and you just did a 5D model and integrated over the extra dimension to get a 4D thing, then you can take in all of the realistic things that you get, you can take the K goes to 0 limit smoothly and nothing crazy happens. Whereas these two in this setup, they look completely different. And all I've done is add this constant. So this at least highlights some one reason why you might be suspicious of just working in the 4D theory. Second is just a more conceptual question. We said that Fc should be proportional to W to get in the vanilla setup. But in the extra dimensional setup there, the W could be in different places in the extra. So we could have a superpotential on the UV brane or on the IR brane, or there could be something which leads to a superpotential in the bulk. So FC is proportional. Which one is it proportional, or is it proportional to the sum? It's not obvious from just working in the 4D theory. And if we said that FC has this universal form for the masses that it gets in anomaly mediation, it's some beta function times FC, and that's true for all of the fields in the theory. But if FC is proportional to this W on the boundary, then how does that lead to a mass for a field on the IR brane?
So going back, I got myself confused again. Sorry about.
No, go ahead.
In 5D theory, are you thinking of it as supersymmetric to start with in the bulk, or
Yes.
so you have n equal to in 4D language n equal to supergravity compact line interval effectively
Yes.
with two branes,
Mhm.
and then the branes you're coupling as 4D fields to that 5D theory, or how do you treat the degrees of freedom on the brane?
So basically, I have n equals 1 theories on the brane.
Okay.
And then I have an n equals 2 theory in the bulk. I'll sort of get to this in a bit. The n equals 2 theory in the bulk, the n equals 2 multiplets split into pairs of n equals 1 multiplets, which have opposite charge under the Z2. And the even ones can also live on the brane, the odd ones cannot. And so that'll be the coupling. Yes, and if another thing, a related thing, so if before I add supersymmetry breaking, the W was giving me ADS space, the 4D ADS space. And so the 4DCC has to be, if I imagine this is ADS5 with an ADS4 at each constant slice in the bulk, the 4D cosmological constant has to be the same everywhere. So how can this, or another question is, how can this come from a boundary W? It can be if the theory is stabilised, but then that requires something to play with the stabilisation. So how do we get this universal form of anomaly mediation from this 5D setup is the main question. And this is an issue of the CC is sort of related to.
But your bulk theory is not pure and equal to supergravity. You have matter principle in the bulk, or
Yes,
yeah.
yeah. I mean, you would need to add things to get the potential anyway, like something like that. Yeah. Yeah. So yeah, and so this is sort of a bit of a toy model at this point of the 5D theory. But in the 5D theory, I have this similar radion, this sigma, which I did. The sigma, the scalar component is equal to R, and I have a no-scale form of the theory in the bulk, and I can so I can add these loop corrections which have this form. So you get a 1 on sigma cubed. Yeah, you get a 1 on sigma cubed loop correction in the Kähler potential, and so I'm integrating over y here, which is the extra dimension. So this is sort of a simplified. This is not the full 5D theory, but it's a simplified setup. And if I add a superpotential, which is just, so I add superpotentials everywhere, then the full W is the sum of the bulk plus the boundary times a delta function, and then the other boundary times another delta function. And I find that FC is proportional to beta times W, and F sigma is proportional to W. So this is kind of the analog of the no scale, the flat extra dimension I had before, except it's been broken by this parameter beta. And then when I do this, I find that the 4D potential is proportional to this full sum squared. And the issue with this is that I get terms in here which are like the delta function of y squared integrated over y. So these terms all both blow up. And so you always get these singular terms. And this is sort of a generic thing. When I have boundary terms, the potential in the supersymmetric setup is always a square. And when I have these delta functions, that gonna lead to sort of bad singularities. So the question is, how are these singularities resolved in a more complete setup? And the answer we'll see is that you need additional fields. So these delta functions here are interpreted as sort of boundary conditions for other fields in the field. That's how we sort of resolve the singularities. But then these W's don't act in the same way as the W on the boundary does not act in the same way as a constant superpotential does in the 4D theory. Right? That will hopefully become a bit clear, more clear later. But you can already compare to sort of the naive result if I just did it in the effective theory here. If I just said that this W, each of these terms just reduced to constant terms in the 4D theory, then I would have this answer for the potential. You wouldn't see the fact that there's singularities there at this level. And I would be getting an ADS space from W0 to W1. But that's not what the 5D theory gives us.
So the statement is no scale on 5D, that's just an assumption.
No, that comes out from.
Why is that? Why should that be true?
I think the easiest way I think to see it is just that you have an R, like if you just think of 5D gravity, in the metric determinant there's an R there, right? And that just multiplies everything. That's where the sigma comes from. So like the square root G is like R e to the minus 4k R. Right? So this R is
Right, but you
I mean
irrelevant corrections to that.
Hmm?
I mean, wouldn't you just naively have expected irrelevant corrections to that? That
yeah, so that's this beta term. This is
you're saying just the loop is the first correction.
that's the first
Okay.
correction. Yeah. So if I didn't include this, then everything would be 0.
Yeah.
Right, but you need to include that.
Yeah, good.
It will generally be.
So you think of it as coming from Casimir, or it could come from some high derivative interaction.
Yeah, I think it's okay. So yeah, so I guess the summary of this bit is there's two sort of issues with the 4D theory. One is that the K goes to 0 limit if the warp case doesn't reproduce the flat case. There's a question of how do I get universal anomaly mediated answers when the superpotential is local, whether it's on one of the branes. And when I do have things on the branes, I have these singular terms, which at least at this level where I haven't introduced any other fields, give you sort of bad singularities in the potential. Okay, but the more complete 5D theory, which we'll go to now, will resolve these issues. So I think, as I sort of alluded to earlier, the 5D theory has an n equals 2 supersymmetry, and that is broken by the Z2 symmetry, which takes y to minus y. So each 5D multiplet splits into two 4D multiplets, which have opposite charges. So in our setup, we'll have the even fields will be the radion, the sigma. And I've sort of ignored all the fermions in listing this. But the sigma has a partner, which is the graviphoton, which is an odd field. There's the compensator comes in on a hypermultiplet, so there's effectively two compensators with opposite charges. So the C, and I'll subscript plus for the positive one and minus for the negative one. And there's also, I'm going to add a scalar field, which will be used to stabilize the extra dimension. And it comes in a hypermultiplet, so there's a positive chiromultiplet and a negative chiromultiplet. And I've highlighted in red here, there's a lot of things going on, but the main things we're going to keep track of is F sigma. This F term will break supersymmetry in the sort of no scale way. There's FC plus, which is going to be responsible for anomaly mediation. And then this scalar phi minus here is going to stabilize the extra dimension. But this is sort of the general form. You have every big n equals 2 multiplet splits in half, and you have even and odd fields. So I should also say that in general, you can, you have for a gauge field, like the gravity photon, it comes partnered with a chiral multiplet in the n equals 2. So for the radion specifically, it has to have this charge, but you could also have a gauge field with positive charge, and then it's chiral multiplet, and then that would give you a gauge field of 40. So there are extra ingredients, but this is sort of the minimal kind of setup that I'm going to use.
I have a question. Sorry.
Yeah.
Why is the scalar component of the odd compensator multiplet vanishing here?
So the compensator's like in the 40 theory, it fixed the scalar component of the compensator to be n plane.
Yeah.
So that fixes basically you write everything as a conformal theory, and then you fix that to break the conformal symmetry. So there's a similar thing here. You have extra symmetries. So there's an SU2 rotation that mixes the C plus and the C minus. And then you also have the scalar invariance. So in principle, you could allow for a non-zero scalar component here, but that would break that SU2 in a different way. So you can do it. This is just a choice. That would just introduce, I think it becomes equivalent to changing some of the boundary conditions for some of the fields, but I forget the exact details. But yeah, so you get to, it's a choice of like, it's sometimes called gauge fixing. I don't know if that terminology is quite accurate, but to fix how you fix scale invariance and how you break the SU2 rotations. This is one choice that I only do with this. Okay. Right. So if I look at this sort of the Kähler function in 5D, in this 5D theory, I have this sigma plus sigma dagger, and it now comes with this the grad y is the y derivative along the extra dimension of the gauge field. So you have this form which is fixed by the gauge invariance. And so this is the 5D equivalent of the no scale. So it has this basically the same implication. You just have this extra grad YV term there. But it's a linear in sigma. And then I have this form for the hypermultiplet. So I have the C, the compensators, and then the physical hypermultiplets. The fact they have opposite signs means you get the correct sign kinetic term for the physical hypermultiplets, but not the compensators. They're not physical fields. And so it's slightly different to the 4D theory, but this no scale sort of structure is the same. And that's sort of the important thing. This GC and GH, so this vector multiplet is a gauge field for U1. And this GC and GH are the couplings or the charges of the compensator and the physical hypermultiplet. So they're in principle different. That's what these two couplings are. And then so the equation of motion for F sigma, again, because this is a linear term, it relates the FC plus, which is the compensator that's going to give us, and that's going to give us anomaly mediation. And it relates it to these other F terms and this product of fields. So it's suppressed by all these field values relative to these SUSY-breaking F terms. So this is the, in the 4D no-scale model, toy model that I had, it just set FC to 0. It doesn't quite do that exactly, but the FC is suppressed relative to these SUSY-breaking terms. And so that's sort of the manifestation of this no-scale form, the fact that sigma only appears linearly, at least at tree level.
So eventually we're going to talk about how this is stabilized, right?
Very good. Yeah, so I want to stabilize, that's the next step. So I can do that by, on the boundary, I'm going to add these, so these J's are constant sources, and I'm going to couple them to phi plus. So I'm going to add a superpotential term on the boundaries, on either one. And then when I solve the F term for phi plus, I get a term which is like the derivative of phi minus plus this delta J0. There are other terms here, including a J pi on the other boundary. But then I can treat this as a boundary condition. So I can solve the F term, so I solve that this is 0, and then this delta function, I can treat it as a boundary condition for the field phi 0. And so I find that, sorry, phi minus. So phi minus goes like J0 times this exponential. And this is sort of an aside, but the ADS scale in 5D is related to this GC. So this phi has this field profile, the SUSY preserving field profile, and it depends on what J0 and J pi are. And the radius R is stabilized such that this exponential, so basically if I evaluate this at y is equal to pi on the IR brane, I get that this whole thing is equal to J pi. So that gives me this, that this exponential of R, which I'm going to write with epsilon, so this epsilon is related to this combination, is given by the ratio of these J's. And I can integrate over the extra dimension and get the effective potential. And so indeed, this is minimized when this is true. There may be a factor of 2/3 I missed out here. Yeah,
I have two quick questions. Is this like a supersymmetric version of Goldberger-Weiss?
that's exactly what it is, yes.
And also, do I have to worry about the stabilizing field somehow communicating SUSY-breaking between the SUSY-breaking sector and say that?
In general, yes, yeah.
Okay.
You have, so yes, I think.
But it doesn't necessarily dominate over like the anomaly mediation contribution.
Well, it depends on the coupling. So like you have this phi plus can also couple the things on the brains.
Okay.
But the phi plus is also, so this is all supersymmetric at this point. So I've solved this F is equal to 0. So I haven't broken supersymmetry. If I add supersymmetry breaking on the brains, that will perturb this solution.
I see.
That will lead to an F phi plus, and then that has to couple the things on the brain. So there's sort of a few steps along the way. So it's not clear, but in general, yes.
You're going to discuss sequester.
Hmm?
You're going to discuss sequester.
I'm more going to be worried about deriving a 4D theory from this that reproduces the anomaly mediation and the sort of difficulties with it. I won't specifically talk about sequestering too much.
Okay.
But this, first of all, so if I look at the 4D theory at this point, I have the effective potential is this, and it's minimized at V equals 0. So I still have flat space, and I have not broken supersymmetry. So this is still not a realistic model. And this just comes out of the 5D theory. So I don't get, what I want is a SUSY preserving ADS solution, so that I can then add some SUSY breaking sector on one of the boundaries and ask how it's communicated to the other, which is the anomaly mediated. So yeah.
Sorry, maybe I missed it. Your J naught and J pi were some like constant couplings that you introduced.
Yes, that's exactly right. So I add a superpotential term on each of the boundaries, which is J.
Right. But in principle, what determines them? Like, are they just some arbitrary thing, or?
They're just free parameters at this level.
So it's like, even though you stabilized moduli, you introduced other free parameters.
Yeah, I think any stabilization mechanism is going to choose free parameters.
Why is it? Why are you getting Minkowski back? Just if you added the Casimir to the no scale for this, or
That's what I'm going to do next.
Yeah.
Yeah. So if I add the okay, and so but before I do that, so if I can reproduce all this in a 4D EFT. So remember this scalar function, this F for the warped case. So this reproduces the kinetic terms for the radion. And then given I know this and I know the formula for the potential in 4D, I construct this like effective superpotential, which has these row dependent terms, which would reproduce this potential in 4D. So I can write a 4D supersymmetric theory and look at these terms and see what I need to get the result from the 5D theory. And this is as you would expect. I mean, I haven't broken supersymmetry. You should be able to capture everything in supersymmetry. There are sort of in principle higher order terms that you would need to keep, but if I truncate to a row to the fourth, then this reproduces everything. Okay. Speed up. Okay, so now I can add the Casimir corrections, and so now I've broken no scale, and I can ask what happens when I add these constant superpotentials, either on the boundaries or in the bulk. When I add them on the boundaries, so similar to what I was saying in the toy model, I get some singular terms. So I have other terms in the potential, but if I just write down the delta squared term in 5D at y equals to 0, then I get this. So if I just go back to the case with beta equals to 0, then I just reproduce the same boundary condition that I had before. I would say that phi minus at 0 has to equal J0, and then I've gotten rid of this term. So I can, now that I've added the Casimir and this W on the boundary, I can treat this whole thing the same way, and then that shifts the boundary condition for phi minus. So now phi minus is not just equal to the J0 that I had before, but it also has a term proportional to W0 and this breaking beta. And now I can solve for the F's as well. So F sigma is now non-zero, proportional to W on the boundary, and FC is also proportional to beta times W on the boundary. So remember, when beta is 0, you recover the no scale form, and this goes to 0. And I can actually stabilize this whole thing even by turning the J's off, just by having constant superpotentials on the boundary. And then I get this potential, but it's still flat space. Okay, so these boundary superpotentials, so in the 4D theory, the constant superpotential gave me a negative energy. It turned on FC, the compensator, and then I could use that to get anomaly mediation and tune that negative energy against some positive energy coming from SUSY-breaking. In the 5D theory, when the superpotential is on the boundary, they source these fields in the bulk. They do not give me a negative energy density. These are all give you strictly positive terms. And this FC is suppressed by this scale of like the no scale. So this is quite different from what you would expect from just the 4D theory. And yeah, I've still got flat space. So if I add some SUSY-breaking on the boundary, I'll end into city space still. So I can't really do anomaly mediation yet either. But I can, yeah, and so this is a very similar form of the superpotential and the effective superpotential, which you need to match the 5D result. So again, so the way this sort of shows up in the EFT is that these boundary superpotentials are field-dependent terms. They're not constant terms. And yeah, there's no negative energy. You don't get, I should also say that these FC and F sigma will couple to fields on the boundaries, and that introduces sort of localized terms, mass terms in general, and these need to be added to the EFT by hand. So you have explicit SUSY-breaking terms in 4D, and you don't have a universal anomaly mediated mass or negative energy. I can add, instead, if I put the superpotential in the bulk, again, FC is suppressed by this beta times the bulk superpotential. F sigma is again proportional to the bulk superpotential. I need to keep these J's, these sources on to stabilize. So if I take the stabilizing potential with the J's and then add this W in the bulk, then I have the leading correction to the potential is given by this. So I do now have ADS space in 4D. It's suppressed by this size of these Casimir energy, these corrections, and it's proportional to W bulk squared. And FC is proportional to W bulk as well. In this case, I do have an ADS scale. It leads, I do get a negative energy from the W in the bulk. FC, up to this warp factor, FC is constant. So it couples universally to fields everywhere in the bulk and on the boundary. And we'll see that this like can recreate the 4D results for anomaly mediation. But you need the superpotential in the bulk, not on the boundary. Any questions about that? So yeah, so I guess the thing I'm contrasting to with all of this is just if I was to take the superpotential as a sum of all of the bulk plus boundary conditions and integrate it over y. So I just have W bulk plus W on the boundary, then which is what people have done to do the 4D theory. I would never really see this distinction, and everything would lead to look the same. But because of these singular terms, which you only see in 5D, these W's better interpreted as sources for the bulk fields, and they don't lead to a negative. To get the anomaly mediated answer, you need things in the bulk. Okay. Yes. Okay. So, which is what I'll do now. So now I'm just going to take the bulk W and then add F terms. Just imagine that there's some SUSY-breaking F terms on each of the boundaries. To tune to flat space, I need to tune this like ADS energy density that I started with before adding these Fs against this energy density that comes from these terms. So this is the tuning to get flat space in the 4D theory after adding the SUSY-breaking. And then I had this FC, which is proportional to beta times the bulk. So this is suppressed relative to this ADS scale. So again, if the anomaly mediated masses are beta functions times FC, but the 4D expectation of what would reproduce the 4D result exactly is that this FC was given by up to this factor of k to the half, this ADS scale squared, but it's smaller than that by beta and the 1 on R squared suppression. So the anomaly mediated masses in this model are suppressed by how much I've broken the no scale. And they're also warped, which I mean is not new to our setup. People have argued why that should be the case in the past. But that means also that the fields on the IR brane have very low scale masses from anomaly. So there's some suppression in the anomaly mediated masses in this model. Yeah, and so this is hard to reproduce in the 4D EFT. There's a couple of issues. One is the fact that you have this scalar function again, which is the 1 minus rho squared, whereas in the 5D theory, you had this no scale form, which was quite important. So the radion, the 4D theory does not reproduce that. So it's not a trivial matching between the 4D and the 5D theory. Also in the 5D theory, this negative energy, this ADS scale here, that term actually is a cross term from F sigma FC, not the FC squared term, which is usually the leading negative contribution. And also, SUSY is broken in these theories by F sigma. So there are all these features which mean that a supersymmetric 4D EFT generically won't capture the 5D theory. So to come up with an effective theory that actually does match this, reproduce the anomaly mediation, I'm going to split Lagrangian into sort of a bunch of terms. I'm going to focus on these terms, which are the Lagrangians for the UV and the IR fields, which I'll write in a supersymmetric way that reproduces the anomaly mediated masses. But then I need to add the stabilizing potential, some boundary terms, and tune the CC as explicit SUSY-breaking terms. So the point is just that this supersymmetric 4D theory does not reproduce everything from the 5D theory. I can construct it to reproduce the anomaly mediation, which is what I do. But then I have to add these extra stabilizing pieces. So from the perspective of the 4D theory, it just looks like SUSY is explicitly broken. And so for the fields on the UV brane, I can Yes, so I have to add this term, which will reproduce the FC, and then there's other superpotential terms which have a VEV of 0, because remember if W0 was non-zero, then it would appear in the stabilizing potential. Skip through this a bit. Not sure how easy it is to follow, but the main point is that the anomaly mediated fields in the UV brane are just equal to this. So the anomaly mediated masses are set by FC and then Planck. To reproduce it on the IR brane, I'm going to define this omega, which was the compensator times the radion rho, and then I can rewrite things with where this omega acts like the compensator does, and then the anomaly mediated masses are set by F omega on omega, which is warped relative to the UV contribution. This is, yeah. And again, I have these extra kinetic terms in the superpotential terms. Okay, so that's the end of the talk. I'll just in summary, I guess the main things are that the sort of matching from the 5D to the 4D theory is not as simple as had been assumed, and particularly because these boundary terms, particularly the boundary superpotentials, source the bulk fields, even if they're constant field independent terms. And in the warped case, the no-scale form of the 5D theory is not reproduced by the 4D EFT, which is part also, if we go back to the toy model, why the K goes to 0 limit was not smooth. That's because the warped theory does not reproduce the no-scale form of the Kähler potential. And supersymmetry is often just broken in 5D. So at the end, when I split up the Lagrangian into multiple terms, I had to introduce explicit non-supersymmetric terms into the 4D theory to reproduce the 5D result. So I should also say that in the paper, we also considered a different way of stabilizing the extra dimensions by condensates. In that case, you can get some times where supersymmetry is not broken. You have a supersymmetric 4D EFT. But I chose to present the hypermultiplets, this Goldberger-Wise type stabilization, because I think it makes clearer all of the issues that we found. So you also need to add SUSY-breaking terms to the boundaries. And then the universal sort of anomaly mediated form that people study and compute comes from the W in the bulk. And that's also what gives you a negative energy density, not things on the boundaries. So I'll stop there.
How heavy the radion? As heavy as the gravity, or lighter, or heavier?
Well, it depends. I mean, you have the potential. So I mean, if I put these J's in, then it's going to be. So this is in 5D Planck units. It's going to basically depend on these J's. In this case, so in this model, it's I guess it's free to choose the mass of the radion by these J's. It's going to be warped, of course. In the case with the superpotential, it's related to these boundary superpotentials. So there'll be some relation to the gravitonian mass in that case. But in general, it depends on the stabilization.
So it can be heavier than gravity.
Yes.
Even if you end up with something that's mixture of the anomaly mediation or maybe radion mediation. So is there MSSM software the gauge mass is still much smaller than the gravity mass, I guess.
The gauge
gauge mass still is one loop suppressing compared with the gauge mass, or is there some?
No, it won't be loop suppressed because I mean, if the gauge units are in the bulk, then it couples directly to sigma.
Let's put gauge on the boundary.
On the boundary, then it'll be loop suppressed. Yes.
In comparison with the gravity mass.
Right.
Okay.
But Yeah, so I mean, one way to get around some of the problems of anomaly mediation, the negative lepton mass grade, is to, if you had some of the gauge fields in the bulk, then they get a direct mass, the gauge units get a direct mass from the radion. And then that can couple to the boundaries. That might also spoil sequester.
Yeah, genome mediation.
Yeah, that's exactly.
But can I rephrase everything here still in the language of 4D conformal field theory and getting strong dynamics in IR and so on, just via the dictionary translate everything in 4D.
Yeah, I think so.
So in 4D, if you do it like that, it's still it will be the same here, right?
Oh, you're saying like I should be able to reproduce
Instead of actual dimensional separation, I was thinking about long conformal running suppressing operators. And it should be the same.
Yeah, but I guess the 40 theory is not guaranteed to be supersymmetric.
Well, I'm just saying I can literally translate everything you do here via the dictionary to 4D, right?
Right, yeah. But I guess the 40 theory may not look supersymmetric.
I guess I had a similar question, which is like, can you, if you've thought about like the 4D dual interpretation of the SUSY-Goldberger wise, and like does it have some nice, I guess it would be a 4D SCFT if there's some nice way to think about it.
Yeah, I guess the Goldberg wise is sort of like, you could just do it as a supersymmetric. It's sort of independent. It has the same interpretation regardless of whether SUSY's broken. I haven't really thought too strongly about the CFT, but yeah, you could. I think like like this, like we could write this part supersymmetrically, but then we had to add all these like soft terms, I guess, or SUSY-breaking terms. So the full 4D theory does not reproduce everything. It's not supersymmetric. It looks like SUSY is explicitly broken. So you could translate the supersymmetric 5D theory into a 4D theory, but that 4D theory may not be supersymmetric. And in this case, it generically won't.
Is that because there's some right degree of freedom? So why can't we write down this intuitive skill? Why can't we have a 4D EFT with a spontaneous breaking? Intuitively speaking.
Well, I think there's just some things that the 4D EFT doesn't reproduce. So there was there's the no scale structure, which means just that when you solve for the F terms in the 4D theory, they're not the same as in the 5D theory. The radion has like a different parameterization, but also more directly, like if I have these terms, for example, so FC, if I have things on the boundary, FC is proportional to a boundary term. That will give masses to fields which are localized in the UV from the compensator, but not to fields in the IR. But in the 4D theory, I have one compensator and it couples to everything. So the 4D theory can't reproduce what happens in 5D, which is a compensator which has different couplings to different fields. At least I don't know how it will reproduce that.
It does sound intuitively strange, though, that you can't deduce correctly. I mean, I wouldn't have thought there's obstruction to doing it. It may be messy. It seems weird. I mean, a lot of your bulk analysis is very similar to heterotic M theory and reductions on the Fabian compactifications to 4D. I mean, they're typically preserving it in the 4D theory.
Right.
But the bulk fields get sourced by couplings on the two walls. The 5D picture is almost identical. except for constraints on the field content,
Yes.
and it has
yes.
more SUSY.
Um,
And you don't get to tune the boundary superpotentials.
Sorry, can you explain the abstraction again you said it was the compensator coupling differently to?
yeah, so if I have this boundary term, then the compensator couples like locally to things in the UV in the 5D theory. So if I imagine just some fields with generic wave functions in the bulk, then it's going to have a different coupling. It's just going to be equal to the wave function at 0. Whereas in the 4D theory, it just it's couples universally, has a well-defined universal form of the coupling to everything. So the 4D compensator can't reproduce this 5D result where this has some locality in how it couples the things.
Yeah, but it's just saying that it's not going to look like a simple compensator in 4D, right? It'll be some more involved model. I mean, I don't see why.
It sort of add some extra spurions or something.
Yeah, there's going to be some
Maybe
extra
that-
couplings
that
also
might be
to suppress the.
Or maybe still non-linear supersymmetry despite the conformal compensator. For example.
Oh, some non-linear.
Yeah,
realized
usually when we
habitat.
introduce conformal compensator, just we can realize supergravity linearly.
Mhm.
That how is to construct the theory. Yes, I wondering in this case for the even in the 4D case it's non-linear. I'm not sure.
Yeah, maybe there's a more complicated supergravity setup with it. You have some can introduce that kind of freedom, but like at least the standard compensator formalism you can.
Yes, this doesn't do it.
And yeah, actually, what you said about the M theory, I think it's quite similar. You have these things in the boundary, but I guess you have a two-form field in the bulk, which is sourced in a similar way to like this Goldberg-wise is. But I think there you usually have a flat, no warping in the extra dimension.
I think it depends on what gauge model you pick for the. You have to compactify the rest of the dimensions, and how you do that will give you some profile, which can induce warping. Oh, sorry, the warping is in the dilettante there. It's not in the metric directly, but in Einstein frame it would be.
I see.
It would be correct from the math.
Because part of the complications becomes much easier to reproduce things in the 4D theory if everything has flat profiles like this. The warp factor and the fact that the Goldberg-Wise has this profile that makes it harder to reproduce things. So that's part.
Before closing, is there other comments, questions? Okay, if not, let's thank Nick again. Yeah.
For some.
Yeah.